So you have heard all about the physics and how difficult it is to understand the meaning of our universe, the origins of mass, and how difficult it is just to do complex physics analysis mentally. But in addition to that, we also need to translate it somehow into the machine level. So, talented physicists need to have a way to go through all the data that they collect and extract some kind of interesting information about physics. So I will tell you a little bit about how CERN is approaching these problems. So how CERN is helping the physicists to get the answers they want, what kind of challenges we have with computing, what could we do to ease this, and most importantly, what kind of resources we require so that we achieve reasonable results in reasonable time. So CERN is the European Particle Physics Laboratory. It was founded in 1954. So the climate at that time was the post-war Europe. It was a really difficult time for Europe because it was still being brought up from the ashes of the war. But at the same time, there was a remarkable spirit of unity. So people have come together, and the United Nations have been founded around that time frame. Many international organizations have been founded around that time frame. And in 1954, 12 countries have founded a particle physics laboratory for Europe. And this was an initiative that was decided to be implanted near Geneva. So it was not itself in Geneva, but it was very close to the city, less than 10 kilometers away. And from that time, it has grown enormously. So now, today, in 2011, we are a really global laboratory, the largest particle physics lab in the world, and probably one of the largest laboratories in the world overall. We have 20 member countries. We have scientists participating from 110 institutions. So this is a pretty large body. And we are doing some of the most ambitious physics experiments to answer the kind of questions that Brian described to you. So we are not trying to find some ephemeric particle just to have the satisfaction of knowing whether it's there or not. Any find that the LHC will have profound implications on how we understand physics. So at the moment, we have around 3,000 personnel on site, more than 10,000 users. This number is fast approaching 20,000 currently. And we have a budget of about 1 billion Swiss francs per year. That might seem like a lot, but if you really start thinking about how much needs to be done within that budget, then it doesn't really seem like a lot. And then again, when we speak to companies like Intel, for example, and we tell them, yeah, we have a $1 billion budget per year, they look at us funny because their budgets are probably 100 times bigger than that. So we cannot brag about that, unfortunately. So the LHC is a huge particle accelerator which is placed in an underground tunnel. So it is implanted 100 meters below ground. It's a 27-kilometer underground superconducting ring, and it possibly is the largest machine ever built by man. So not just the size of the installation is what is bringing it to this complexity, but also the way it needs to be interconnected. Every part needs to be checked. This machine is basically a prototype of itself, and it needs to run at the first time. So my boss very often makes this joke that this is like an A0 stepping for a processor. It has to work. That's it. There is no other choice. So we have 40 million collisions per second inside the LHC. So particle beams travel in opposite directions, and they collide 40 million times per second. And the whole thing consumes between 150 and 200 megawatts of energy. So this is a pretty significant power consumption for a single machine. You could say that a medium-sized city would consume the same amount of energy. And in probably 10 minutes, I'm going to tell you, okay, so the power consumption of the data center is about 3.5 megawatts, and we are really worried about it. It's so much and so on. And you might think to yourself, why do these people worry about 3 megawatts if they have 150 or 200 megawatts at their disposal? And the reason is that our data center is placed in a very unfortunate place, and we cannot bring more power on site. So if we had unlimited power from computing, things would be very different. But since we do not, we have to really navigate through all the difficulties through which many other companies and labs have to navigate through. So the LHC is placed underground. This is the ring. You see, this slide was already shown before. And there are 4 experiments along the ring. They are ATLAS, CMS, LHCb, and ALICE. They all are monitoring proton-proton collisions. Some of them also monitor collisions of heavy ions like lead. But they have slightly different purposes. So ATLAS and CMS are 2 detectors inside the LHC that are probably looking for similar things, but LHCb and ALICE have a slightly different purpose. So it is true that scientists compete with each other and scientists from both experiments compete with each other, but in many cases they also look for slightly different things, and they certainly do it in very different ways. So these collaborations work in different ways, and they are independent of CERN. So it means that these collaborations are truly worldwide and are not restricted to European nations, and that's how we have people from over 110 countries working. So there in the back you see the Mont Blanc, Lake Geneva, and then Geneva itself, which is placed very close. There's an airport nearby as well, so it's a very good position to do research and to have an international collaboration. So this is CERN's accelerator complex. The injection chain is not as simple as just streaming protons into the accelerator or whatever you would call it. They need to be accelerated through a series of accelerators. And then the proton beam is being passed from one to the other, then accelerated a bit more, and then to the other, and so on and so on. And only at the end do the protons end up in the LHC. So this is this blue ring in the middle. And now I'm going to show you a video of how this is actually done. So you see that the protons are being accelerated in a small accelerator called the booster. So they are later passed to the proton synchrotron, which accelerates them to an even higher energy. Then the superproton synchrotron, which is the last accelerator before the LHC. And then they enter the LHC. And the LHC is supposed to accelerate them to 14 teraelectron volts, 7 per beam. So this is the LHC tunnel. You see that the blue construct in the middle is the shielding of the beam pipe. So it carries superconducting magnets. And then particles travel at a speed close to the speed of light. And then they collide in underground detectors. So the detector is actually the machine that gives us the readout, that gives us the information about what happened during this collision. So here you see 2 protons colliding. Of course, we aim proton bunches at each other, not single protons. So there are billions and billions of protons that actually collide or that cross each other, but only a small fraction of these protons and the beams collide. So then we move on. Okay, there we are. So these detectors are really huge machines. They are cathedral sized. So you could easily imagine a huge building like a church, and these things weigh about the same amount of, have about the same mass, have about the same size, and they were all lowered underground either in pieces or in bigger parts. So in this case, you see the lowering of the CMS detector. So some single pieces of this detector weigh 1,200 tons, and they were lowered in one go. And then the detector is later assembled underground. So if you take a look further, you see the lowering process. During these lowerings, the distance between this huge machine and the border of the pit was about 2 centimeters. So there was, if you shake this thing just a little bit, you not only ruin your wall, but you also ruin this thing that thousands of people were building for many years. So it was a pretty precise operation. Then these things end up in underground caverns. So these are very sophisticated constructs. There's a lot of security. You need to make sure that there are no people inside when you run these experiments, because the whole thing becomes radioactive for short amounts of time. This is not heavy radioactivity, though, so it's not a problem. We can enter very quickly after we switch off the beam. Up there, you also see fire extinguishing systems and so on. So this is a pretty big undertaking. And this detector is key to understanding what happens when 2 protons collide. What happens if we accelerate them to a high energy and when they collide. So the idea is that you probably want to take pictures of these collisions, and these detectors are nothing more than just huge sophisticated cameras that can take pictures of what is happening inside. And you could think of them as cameras that have really many pixels. And the difficulty is that all the pictures that you take are blurry. You don't really see what is happening in the picture. You need to tune the focus very, very well to be able to understand what's happening. You need to take many pictures so that you can understand what is on those. And moreover, you need to take those pictures 40 million times a second because you have collisions 40 million times a second. So this is a pretty significant challenge. And on top of that, you would like to throw away those pictures that show something that you have already seen. So if these pictures show faces that you have already seen or people you have already seen, you just throw them away immediately. You are not really interested in keeping them. Maybe you keep some of them, but you are truly interested in finding the people or the things that you have not seen before. So this intense data pressure that we are getting out of this machine, these huge readouts create very strong demand for computing. So the raw data rate, according to different estimates, could be even a fraction of an exabyte per second. So it could be even a double-digit percentage of an exabyte per second. This is a lot, and keep in mind that this machine was designed 15 or 20 years ago. It's not that people today realize, oh, we're producing a lot of data, we need to process it. People designed this knowing that it's going to produce this amount of data and expecting that computing is going to be able to take that load. But one event, one proton-proton collision is only 1 megabyte. So how does it relate? I mean, we are truly interested only in a small fraction of these events, not in all of them. The interesting part is maybe 1 megabyte per event, and yet we produce a fraction of an exabyte per second. And the answer is that this is in reality a statistical process. So out of all the background, we need to extract what is really, really interesting. So we store about 15 to 25 petabytes of data per year that are actually interesting. So this is something that we keep, that we are going to write to tape, and that is never going to be thrown away unless we really think that we understand everything. But even with older experiments, we think we understand things, and we still decide to keep the data because we come back and then we recheck for things that we have discovered since then. And to that end, we are running 250,000 Intel architecture computing cores, so they are not at CERN, obviously, but the Large Hadron Collider Computing Grid, which is a distributed structure that runs the computing, has 250,000 computing cores that help the physicists understand the data. So as I told you, out of this immense pressure of data, out of this fraction of an exabyte per second, we store only 15 to 25 petabytes per data per year. So we want to understand what is worth keeping and what is not worth keeping. And a rigorous selection process enables us to find that one truly interesting event in 10 trillion of events. So this is the kind of data selection rate we're speaking about. This is how special this thing is. So it's not like looking for a needle in a haystack. It's probably like looking for a needle in a million of haystacks or something like that. So this is an animation that shows you what is the data selection process inside the detector's computing system. So close to the detector itself, we typically have either dedicated hardware, so these are FPGAs or specialized circuits that try to establish what kind of data is incoming and whether this data is interesting or not. And this data is being pumped into buffers, into some kind of decision buffers. And they're accumulating this data, in some kind of a pipeline. And this could be, okay, we have seen a decomposition of particles that we know very well. It could be that we see a decomposition of particles that we have not yet seen, and it needs to be photographed. So later on, when this pipeline reaches, let's say, maturity, when there is a decision taken, because we always need some time for decision, it typically is a microsecond or maybe 2 microseconds. The decision from this decision-making device, let's say, it's called a trigger, is saying, yes, we want to keep that data, and then suddenly we need to write down everything that was seen at that moment. And if we don't see it, if we think that this is something that is not really that interesting, then we know that we can throw this away, or we can only record a part of this data, like kind of let's take a shortcut and not write everything down. And then the really interesting parts end up in storage. So you see that here. This is the storage, and then everything goes to the data center for initial processing. So From that, we really select a very small fraction of the data. So this huge data stream, which could be even hundreds of petabytes or 100 petabytes per second per detector, is reduced to something which is only a gigabyte per second or something like that. So it is greatly reduced. And then we move on to the discussion of the whole data flow. So this is this data that is being produced. So you have a stream of several gigabytes per second. What happens to it further? You gather it in the detector, so there's online triggering, and this is what we call the online part. So this is the kind of computing that happens very close to the detector and happens under the pressure of time. And then opposed to that, we have offline computing, which we can conduct in our computing farm, which we can just run at our leisure, even on workstations if we please to do so, and it's called offline. So there is a distinction between those two worlds. One is under the pressure of time, and it's a bit closer to HPC, or what people understand as HPC. And then we have offline, which is closer to what people understand as high throughput computing. And I would say that the vast majority of what we do is high throughput computing. So we have online triggering and filtering in detectors. And we also have event simulation. So we also simulate events. We create artificial detectors in software. And we try to understand the physics processes that we designed. From that, we move on to the reconstruction phase where we try to reconstruct the events. So we combine this data that we simulated with the data that we have actually gotten from the detector, and we try to understand what it represents, what it shows. Does it fit what we think it fits? Further, we move to event reprocessing. And from selection and reconstruction, this reprocessing stage, we get event summary data. So we already can throw away a further 90% of what we have seen. So in that process, in that further understanding, we can say, okay, 90% of what we found is probably something that we know very well, so we're gonna try to get rid of it. And then we have data analysis. So this is something typically conducted and commandeered by physicists, and they try to understand particular sections of this data. So in a typical case, a physicist is going to work on only a small fraction of this data. So only, again, a 10% section of this data is going to be something that the physicist sees and analyzes. So in the end, out of the 100% of raw data, so these gigabytes per second, you end up with small analysis objects, which are several hundred of events. Let's say, small files of 500 megabytes or I don't know, 50 gigabytes, something like that, that constitute analysis objects. And this is something on which a physicist can work. It means that a physicist can take his workstation, copy that file to his workstation, and later analyze the data against known physics that he has either designed or that he knows exists. And before we move on to the hardware part, which I think you might find the most interesting, I would like to digress a bit into CERN software. So CERN software is something that drives the hardware that we are using in an equal way as the constraints and requirements that are just coming in from the data flow. The first thing is that we have millions of lines of C++ code. I'm not going to discuss whether C++ has been a good choice, because this is something really debatable. And those of you who have large C++ frameworks know very well what I'm talking about. Going with Java most certainly would have been much worse than that. So for the moment, we are running with C++. We are struggling with all the issues that come with it, and the fact that we have a lot of code. So you can imagine that if we run a software framework which has 4,000 shared libraries, there's going to be a fair amount of memory being used, a fair amount of switching, context, and so on. So this is already quite challenging to have that, to manage that kind of complexity, and to be somehow efficient in that. And again, there's no good way to find out if we're efficient in doing that, because we don't really have any kind of way of understanding that, because the thing that our physicists are supposed to do is to do science and not necessarily to be software programmers. So that's, again, another thing that is a difficulty. Then the key foundation in that case is Linux and GCC. So our offline computing farms run Linux almost entirely. We also use the GCC compiler, but we also are taking a look at other compilers, because this is not the only one that is, let's say, interesting and that could deliver good results. We know that our compute scales with a combination of specfp and specint. So in reality, the benchmark that we use is the C++ subset of Spec 2006. So this is the defining benchmark that we use for supplying to our vendors and so on. And it helps us to understand how the systems are doing. Another thing is that our events are independent and parallel. So any kind of data that is coming in from the detector can be processed in a parallel way. So we have parallelism inherent in the problem. It's there, and it's up to us to use it. And unfortunately, we are not using it for the most part. So we are doing process parallelism, and that's what enables us to scale to 250,000 cores. But we are not using shared memory parallelism or anything like that that would enable us to save on memory. And this is also a problem, which I will discuss later. So as I said, we need little or no HPC. So we do mostly high throughput computing. We do not necessarily require high performance computing. We do HPC for example, engineering analysis or some kind of fluid dynamics and so on. But for the most part, throughput is key. Throughput, be it in compute or be it in I/O. And we will see a bit later how that maps into the architecture. So we have very large aggregate requirements. This amount of data creates a very large aggregate requirement. And the workload is chaotic. So you don't really know what level of support should this carry. So you don't know if you need to supply 200,000 cores or 100,000. Maybe before an important conference, you need to supply 400,000 because this is what physicists need. And physicists are typically very greedy creatures. They will use any amount of computing that you give them. So you also need to gauge that and to try to find out what is the real requirement for that. How much can you supply so that everybody's satisfied and that we get reasonable results and that we actually end up with a manageable structure that does not leak too much cash that is being put into it. And on top of that, we have Moore's law. So we know that our requirements grow with time. Probably the rate of growth is slowing with time as we understand the machine, as we understand the software that is driving it, and that is processing the results. And we know that the amount of transistors is growing linearly on this logarithmic scale, so we can expect more and more from companies like Intel, and they keep delivering. But clock speed, which is shown on the blue curve, is not going up anymore. So we have historically always relied on clock speed to increase our processing speed, and this increase in performance could be translated to many things. You could have better physics processes through that, so you could understand more about your physics. You could run your software faster, or you could have other gains. But this free lunch is over. There's not much you can do now, and either you move to many-core or multi-core, or you can't do too much. For the moment, we're fine because we use multiprocessing. And we do take advantage of this parallelism in the hardware. So it's not like we are using just one core of a great Intel CPU and then we do nothing with the rest. No, we use everything we get. But there is a limit to that scaling as well, and we need to think ahead to the future. Because today, if we have 30 cores in the machine or 60 cores in the machine, that means that in several years we're going to have 100 or we're going to have 1,000. And we're going to need to think whether the amount of memory that we need for that is going to be actually available, and whether a platform with that much memory is going to make any sense. And we all know that different technologies do not progress at the same speed as a CPU development. So in order to cope with that demand and in order to cope with this pressure, we have developed something called the Shift architecture. It's this scalable heterogeneous integrated facility. This is an architecture for data processing that won the Computer World 21st Century Achievement Award in 2001. And it was designed much before that, and it is still used to this day. So in this architecture, which is the basis for our Tier 0 data center, we have CPU servers. So these are basically tasked with doing standard kind of processing, compute-bound jobs. We have disk servers, which serve as an intermediate buffer for data. So we stream all of the data that we get from the detectors to disk, then we process it, and then it ends up on tape. So we are running a pretty large tape library. We have a requirement of 15 to 25 petabytes of storage per year. And that typically grows as you want to have multiple copies, you want to rewrite some tapes, and so on and so on. All of that is interconnected with a simple backplane network that is Ethernet. So we run 10 gig Ethernet between the most important parts, and all the rest runs only 1 gig Ethernet. Because one event in high-energy physics is typically around 1 megabyte. So that means that in order to do some kind of useful processing, you just need 1 megabyte of data. And with that 1 megabyte, you can do quite a bit. So we don't really have large aggregate requirements for networking. But as we will see later on another slide, it's a bit more complicated than that when you throw in other things into the mix. So the central tier 0 computing farm is what supports CERN, what is dynamically supporting CERN's computation, what is analyzing the data as it comes from the detector, and it is preparing it to be written to tape, to be sent off to other centers, and so on. Because if you have 20,000 people collaborating on the same data, you need to make sure that it's available to all of them. And I know that this is not a challenge for Facebook or Google or anybody who has 500 million users. But for this sophisticated science processing infrastructure, it's a bit more of a challenge than just enabling to see somebody else's profile. So we have an old retrofitted main computing center building that has 2 floors. It was built for mainframes in the 70s. And in it, we have about 8,500 systems. We run probably 60 to 65,000 cores. And we have about 60 petabytes on disk and 70 to 80 petabytes on tape. So depending on whether you use compression or what kind of technology you use for tape and so on, we have 70 to 80 petabytes on tape. Tape is a pretty big topic at CERN. And we have chosen tape because this is the technology that gives us very good cost efficiency. And most importantly, it gives us very good guarantees on the integrity of the data. So in a disk, you always have moving parts. Disks fail. And it is not really a good idea to keep a lot of your precious data on disk because this disk might one day fail. And even if you have different RAID systems and so on, you could lose something. So we try to minimize the risk of data loss. So we put most of the data on tape. We also ship it off to other data processing centers for copying. So all in all, we have several copies of the data that we collect. The tapes are being rewritten regularly. And the target for, I think, next year is to achieve a twice per year rewrite ratio. So we would rewrite the whole data that we own 2 times per year and check it for errors. This is how much we care about the integrity of the data, because any discoveries that we might make are in that data. So, a potential Nobel Prize or the lack of it depends on the data we have and depends on really every single file. I mean, statistically speaking, if we lose some files, it's not a disaster. We can recover from that and we can analyze the remaining data. But physicists really, really do not like it when data gets lost. Then, as I told you, we have a 2.9 megawatt limit for power consumption, and we cannot bring any more power to the site. We are now in the process of making an extension to 3.5 megawatts. But the problem is that the power lines cannot carry more to that site. So the accelerator itself is powered through a different set of power lines that come directly from France. They do not come from Switzerland because our laboratory lies on the border between France and Switzerland. And I work in France, but I go to Switzerland across the street to eat my lunch. And this bizarre situation has led to a point where we either can grow in another data center, or we can build a new one, which costs a lot of money and probably nobody wants to shell it out. Or we can just try to expand and maintain some kind of reasonable data efficiency. So since several years ago, data efficiency has been a huge topic for us because we are just power constrained. And even though we have the money, it doesn't make any sense spending it because we cannot put more equipment in the racks. So in some places of the computing center, we only have 5 or 6 servers at the bottom, and that's it. And the rest of the rack is not used. So the 20 meters of vertical space are occupied on only maybe 30 centimeters or 50 centimeters, and that's it. So power efficiency is a very big problem. And then we have probably a 4.8 terabit switching capacity. So we have a network node in the middle of the room. In fact, it is seen on this photo. So if you look carefully down there in the back, you see these yellow pipes. So this is for fiber optics. Networking is a very important part of our installation because we rely on exchanging the data, on copying it to different sites, and physicists from all over the world need to be able to exchange it and to collaborate on it. One other thing to mention in the context of the data center, I think, is virtualization. We are not really interested in virtualization for efficiency because we typically run jobs at the 90% or 80% efficiency. So it means that 90 or 80% of the CPU is used at any time. But virtualization is interesting to us because it carries the promise of efficiency when it comes to dealing with different configurations. So we could envisage a scenario where we just swap VMs whenever we want to swap jobs. So currently, we just use a single operating system, and we supply different processes in it. But it could be that every single experiment and every single person who is running some kind of job there would like to have a different configuration. As he's going to supply a virtual machine, and then this virtual machine is going to run and provide him with the functionality of configuration, of free configuration. Today, you cannot really do that. But in case of efficiency, this is maybe not so interesting to us. The other big topic is also security. So as I told you, we are very, very focused on keeping the integrity of our data intact. So we are also interested in the fact that nobody meddles with it. And CERN is also a high-profile target. So you have heard today all about cyber war and dangers of persistent threats. CERN is subject to more and more attacks every day. So this curve is growing very rapidly. We did not get that much attention and interest several years ago, but these days it's quite important. And in one case, we had a breach of the web server that was, I think, not even at CERN, but somehow was in the CERN domain or something, which was serving some data for an experiment. And the breach of that web server, which was somewhere externally, was interpreted in the press as a breach of all the securities of CERN, and we have been hacked. Period. That's it. And you don't really. There is no easy way to respond to that statement. I mean, it's true, right? It means that something in our network was hacked. Whether it was important or not is a completely different story, but people remember that. So it is very important for us to minimize the amount of these incidents and to keep a lid on things. So we are also putting a lot of attention to security now. Everything that we are running is built of commodity components, or we are trying to build it out of commodity components. So I'm very sorry, this is a disappointing slide. You are not going to see any exciting technology here. This is something that any of you can just buy in any shop. In fact, you could probably just go to a computer shop in London and buy many of those things off the shelf. And on one hand, it is interesting to know that CERN has been always on the forefront of computing. And when people didn't even have calculators at home, CERN was already pioneering computing. We had supercomputers. We were programming them, working with engineers from companies like Digital on making those computers run efficiently. But with time, as computing proliferated and as the world became more and more surrounded by ubiquitous computing devices, this kind of effort that is at CERN lost meaning. But for us, it was good news, because that means that we can really go into the store, buy some stuff, put it in our computing center, put it in motion, and we're done. We don't have to worry about anything. We don't need to invest a lot of money into personnel that is going to program those machines. It just seems to happen seamlessly. So in this case, we have, well, there's one exception, that is electronics. So everything that is really close to the detector needs to be radiation hardened, needs to be resistant to different kinds of faults, because radiation is something that can very easily cause a bit to flip in your memory, and then suddenly you get a fake readout. Or you need to realize that this is something that is not really making sense. But in case of CPU servers, this is completely standard. We do periodic procurements. And we typically say, we would like a server that provides this and this amount of computing power, and give us whatever you think is best for the price, or for the level of servers that we're going to get. And it just happens that most of these servers are ending up as Intel. And I would say that the vast majority of those servers are ending up as Intel. So we don't specify which AMD or Intel we want. We just say we want this amount of computing power for the best service and best amount of money that we can buy. And then we have a fixed requirement of 2 gigabytes of memory per core. So our setup, or our agreement, is that we will have 2 gigabytes per process, which means that we have 2 gigabytes per core. So if we buy a 48-core machine from AMD, then we need to supply a corresponding amount of memory. And that is becoming a problem. And I think the CPU makers are also seeing it, because instead of reusing that information that is already in the memory, we are not doing anything with it. We're just copying it again and again and again. And the fact of the matter is that when you run a high-energy physics processing framework, most of the data that you have is read-only. So you only want to change a very small fraction of that data. That's it. And out of that, you will probably have, I don't know, between 50 and 90% as read-only. That means that you are actually replicating 50 to 90% of that memory. And that means that technologies like multi-threading are very important to us. and we would like to take full advantage of them. It's going slowly, but it's coming along. In terms of disk servers, so those that buffer the data that is coming out of the detector and is going into the farm, we have very simple processors, a couple dozen drives, that's it. Again, no magic here. It's all really simple. Tape servers are important, but again, very standard. So we have standard tape libraries from manufacturers like Storage Tech or Sun or Oracle, whatever name you prefer, or from IBM or from anybody else. And tape is our key means of reliable storage. So it needs to run well, and we need to be sure that this is giving us reasonable results when we read them back. In terms of network, these are fiber optics and standard copper Ethernet. So this is either 1 gig or 10 gig, whatever is more important at the moment. So compute servers typically are connected by 1 gig, but tape servers and disk drives are connected by 10 gig. And in terms of software, we do our own software for all the computing. So we have several major processing frameworks. We run on Linux and GNU. We have some Oracle databases. So for example, you can understand that when you have this kind of precision, which aims at understanding where a single particle is going, you are going to see that the detector is moving in 3D space as Earth is moving. So the Earth's crust is in constant motion. There are vibrations and earthquakes and so on. So at any single point in time, you need to understand where the detector is in 3D space. Otherwise, you don't know where it was with relation to the beam, and you don't know if the particle that you're actually monitoring is the same one that you have seen a minute ago. So for that, we have, for example, a conditions database, and in that conditions database, which is built on Oracle, I'm not sure if there's any meaning in that. It might have been something else, but Oracle was chosen. We store the 3D location of the detector at any given point in time, so that later we can reconstruct the data and we can understand what it was representing. So these are the kind of challenges. You know, you see something moving very slightly, or you see an earthquake in Japan, or something blows up, and suddenly you see the detector moving around. So everything is built on commodity components, and I could tell you, okay, we're done, we're fine, we have these thousands of processors, but the fact of the matter is that we don't have enough money to do all that. So even with the budget that we have, we cannot really afford to have that kind of scale of processing. When we were designing the LHC, we knew that we need some kind of smart computing infrastructure so that we can share resources and so that we can fully supply the computing power required. So we expected 100,000 cores being necessary to process this, or 100,000 computers, because we didn't know that multi-core was coming. And with time, this requirement also grew. But we had a structure in place, which was already thought of in 99, and then later made more precise and elaborate in the 2000s. And this is the Large Hadron Collider Computing Grid. So basically, it's an interconnected network of processing centers. And what you do is you insert your workload into this network, and you don't care where it is. Okay, it's like a potluck lunch. You supply something, you supply some computing resources, and then you put your workload inside, and then you get the answer after some time. Now, this sometime is, of course, the topic of many battles between computing engineers and the physicists, because it could be several hours if you're in a priority queue, and it could be 2 weeks if you are out of luck. So it is important to get a good place in the queue always. But the main point is that what you're really doing is you're submitting your data to a huge distributed structure, and this data is being processed somewhere in the world by some computer. So you don't know what architecture it is. You don't know what it really is doing. You just know that it's Linux. It's maybe x86 or, well, you know that it's x86, but maybe it's 32-bit, maybe it's 64-bit, and so on. And then you get the result. And you don't really care about how it's going to develop. And this idea of this computing grid was developed long before the cloud was even thought of. So many countries collaborate in that structure. We have probably 35 countries collaborating in this case. We have the Tier 0 Center, which is CERN. So there in the middle, we do the initial processing of the data, like the really simple stuff. Then it gets sent off to one of the Tier 1 centers. So these are major collaborating centers, which are providing the majority of the computing power in the grid. So CERN, with its 64,000 cores, is not the majority. The majority is coming from the Tier 1 and the Tier 2 centers, which are kind of satellites. So the real action happens there. And Tier 1 store the data permanently. They reprocess, they massage the data so that it's stored properly and so on. And then we have simulation and end-user analysis happening in Tier 2 centers. So these are typically smaller clusters of 60 or 100 machines or something like that. We have nearly 160 sites, so nearly 160 different places where infrastructures are participating in this effort. It's a global effort. We have probably 250,000 cores, 160 or 170 petabytes of storage available, so again, quite a bit, and over 1 million jobs per day. So over 1 million separate programs are being executed and are delivering results per day. That's quite a bit. And the amount of users is not so high, so the amount of users is probably in the order of 10,000, which makes the amount of data on the grid probably several terabytes per person. So a single person owns, let's say, several terabytes of data. All of this is interconnected with high-speed links. So to all the tier ones, we have dedicated 10 gigabit links by fiber optics. And sometimes they're quite actively used, sometimes they're less actively used. We have backups for all the links, not necessarily at 10 gig, but sometimes at 2 gigs or 1 gig. And there's a range of collaborating institutions. So it is not only in the interest of CERN to do that, but also in the interest of those institutions, because that enables their scientists to access the grid, not only for high-energy physics science, but also for many other sciences. So these grids are typically a part of a larger structure or a larger organization. So Europe has one of these, and the US has another. And they collaborate together on many different sciences. So high-energy physics is just one of the sciences that uses grid computing, but there are many others. And then there's the question of the cloud. So I guess, you know, if you ask companies like Intel or many others, what is fashionable, what is the hot topic right now, they will tell you immediately cloud. Cloud computing is great. Cloud computing enables you to do anything, and so on and so on. But for us, it's a bit of a mind-bending problem because, first of all, I already told you how important it is for us to keep data integrity. So this data is our most sacred possession. We really need to make sure that it is kept properly, nobody tampers with it, and so on. So in the cloud, we have problems like data persistence, access to the data, who has access to this data? Are we sure that if Facebook or Amazon or anybody else keeps our data, that nobody's going to have access to it, just us? Then there's jurisdiction. What if, for some reason, we do not wish governments to look into this data, or we do not wish them to change it, or we do not wish them to administer it in any way? So again, this creates many, many problems. I would say that this already is a very significant barrier for us. We probably will move to the cloud with time, and we will solve these problems, but these are pretty significant. Then there's the question of guarantees. So, okay, we have submitted our data to Google, and suddenly, let's say, a data center blows up. Okay, there's a huge fire, and we learned that we have lost 30% of what we stored there. What do we do with a problem like that? Do we rerun the LHC? Do we convince the European Union to shell out another 10 billion euros so that we can build another accelerator? I don't think so. So, again, it is very, very important for us to make sure that we are not losing what we have worked for so hard. And then interoperability is also a topic because currently we are running grids and we are running grid computing, but we will need to make the cloud interoperable with the grid computing. So we will need to move in slightly to the cloud and then maybe creep out to it and use more of its resources. But it's, again, a complicated problem. Then I wanted to show to you how important of a topic computing is at CERN, how seriously it is taken. I will read you this passage from the CERN computing newsletter from the 80s. It says, an electronic mail chain letter has recently been intercepted at CERN. Not only is such foolishness a waste of time and money, yes, electronic mail has to be paid for, but also the superstitious nonsense in chain letters about bad luck if you break the chain might actually worry some people. If you receive such a letter, please have the common sense to break the chain and send an appropriate comment to the person who wasted your time by sending it. So you can see that computing at CERN is serious business. People were reprimanded officially for sending chain letters and for wasting email, which uses precious resources. And in that sense, in that spirit of seriousness, we have some accomplishments which are probably notable. So in '89, we have had the first high bandwidth transatlantic links placed in Europe. So CERN was one of the pioneers of IP and TCP in Europe. Europe was traditionally opposed to IP and TCP, and CERN has entered that domain with vigor and has worked very hard to make IP and TCP a reality in Europe. The World Wide Web was invented at CERN in '91 by several very bright researchers. Sir Tim Berners-Lee is one of them, who now works in the UK. The grid vision materialized in '99, and then several years later, we already had the first working prototypes. In 2001, we have won the Computer World 21st Century Achievement Award for the Shift architecture for our data center. In 2003, we beat several Internet 2 land speed records. And then in 2008, WLCG became the world's largest grid. So there were several grids being built, but in 2008, we have surpassed them all. And in 2011, we are already delivering some very intense challenges for data. So finally, before I conclude, I wanted to tell you about the research initiatives that CERN has with private companies. So we have something called the CERN Open Lab, and I am a part of it. So I work as a staff researcher at CERN Open Lab. It's a unique research partnership of CERN and the industry. So we work very closely with private companies on advancing solutions for the LHC, advancing computing solutions for the LHC. So currently, we have signed up HP, Siemens, Intel, and Oracle. Not in order of importance. And we would like to advance with them solutions which make their products work well in our environments, but also which enable us to use really the cutting edge technology which is supporting the LHC. So the partners support manpower and equipment in dedicated competence centers. We have a separate area of focus for every partner. And we deliver published research and evaluations based on the technology. So it means that we are really working hand in hand with those companies on a daily basis, working on making computing better for them and for us. And the setting is very challenging. The reason we get so much interest from partners is because we have a very challenging setting, and it's very unique. We have a lot of data to process, and we need to take care of it in a very special way, which is quite different from, let's say, the usual way that people use computing systems. We also have a hands-on training program, which is quite robust. So we do education, not only research, but also education with our programmers and with our staff on how to make efficient use of computing. So be it multi-threading or be it performance optimization, we do courses on that. We have a summer student program. We do computing schools. And Huawei has already signed up for the next phase, which is starting in 5 weeks. So we have all the partners who were working with us previously here continuing, and Huawei, which will be a contributor in 2012 for at least a year. On that subject, we have a very lasting partnership with Intel, who is helping organize this event that which you're participating in today. They have continuously supported us since over 10 years ago, so it's a very stable partner. We have a wide range of R&D activities that touch on data center, networking, performance optimization, many core technologies. And out of the most recent successes, let's say, we can say that we were one of the first partners worldwide of Intel to start work and deliver results on the Mike architecture. Probably all of you have heard about the Mike accelerator, which is an x86 chip with dozens of cores that has very wide vectors and is very well suited for scientific processing. So there we have had quite a bit of action, and we have reported good results already at this year's IDF. And Intel is hoping to bring some kind of product, I think, in 2012. And we are adding exascale, cloud security, and embedded processing to the mix in the future. So then we have the final question: what is the future for CERN and the LHC? One very big topic is the amount of data that we're going to process. It could be that due to the upgrades to the LHC that are going to be introduced, we're going to have maybe 100 times the amount of data we have today. Nobody knows how to process this. So we need to think very much into the future, not only in terms of our strategy, but also in terms of the technology that will be able to take this load. How do we scale? Do we scale up? Do we scale out? Maybe there is something else that we should be doing. These are pretty complicated questions, and there's no easy answer to that. The other thing is that the peak of scientific output from a project like this usually comes when the project is coming to an end. So when we are actually finishing to take the data, we will have the highest rate of scientific output from that project. So that was, for example, the case of the lab, the previous accelerator. And there is no reason to think that it will be different in this case. So these are pretty big challenges that need to be solved, not just at the computing level, but also at the strategic level that many other people think about, not just us computing people. And then you throw Moore's law into the mix, and you think of how far will Intel's technology scale, how far will AMD's technology scale, will the manufacturing process that they have in 2018 support an exascale machine? Will we reach exascale in 2018? And I think all these questions together form something that is very inspiring and enable us to look into the future with a lot of interest, but also a lot of focus on what will be the next step for us. We know already that during the major shutdown of the LHC, which is planned in 2 years' time, we will upgrade the energy to the original design. So we will be bringing the accelerator to the full power, so to speak, and we will also make additional improvements. So we already know that there will be more data. But the question is, what happens when you go far beyond that? What happens in 2020 and so on? And that is being defined as we speak, outside of this room, obviously, but a constant process is taking place, which is looking very much into the future. Thank you for listening, and I think we are now moving to a Q&A with Brian Cox and myself.
Thank you. Thank you very much, Andrzej.